All right, so what we're going to do in this short video is we're going to try to work on some linear correlation, linear regression using R. So here we have a couple problems that we can work on. This is just a couple problems here in genetics that says that we're going to try to investigate whether the length of a specific gene segment, so we're going to call that GL for gene length, is correlated and can predict or is in any way useful when investigating the expression level, over here, the expression level of a particular protein. And we have the data right here, and that's the data we want to put in R. So let me go ahead and put that in R. This is just randomly generated data, set seed 1, 2, 3, set seed so that we all have the same data. And then I'm not going to go into the specifics of just how this data is generated here. It's, I just want data. And if you have to enter all your data by hand, so be it. You probably need a slightly different video for that. For us, we have all of the data just by typing these lines. So we have the gene length data. Okay, I see the gene lengths are kind of in the 1900 to 2200 range, and the expression level of the protein is around 200. So the question is gene length correlated with protein expression levels? And more so, can you predict if somebody gives you the gene length, could you predict the expression level? That would be nice if you could do that. So here's what we'll do. Uh, Going back to the worksheet here, find the linear correlation. So the linear correlation in R, maybe we look at a plot first. So you look at the plot with plot. Now, which one do you want to enter first is the one that you think may predict the other one. So the gene length comes first, then protein expression. And okay, there we go. It's looking, this is looking pretty correlated, and it's a positive correlation. So the more that gene length is, the more protein expression we're getting. So a positive, somewhat linear relationship, or very linear. Uh, in terms of how linear this is, we're going to leave that for R to determine. But it's just from the visual, it's looking somewhat linear or pretty linear, and it's positively linear. So so let's see. If you go back to R, you do correlation, core. That's immediately going to give you the correlation right there. So in our worksheet, if we want this to two decimals, 0.70. So that's actually a pretty strong correlation. Um, Now the next question says, is the correlation or the linear correlation coefficient significant? Give the p-value. That's a hypothesis test. And they do have capability for that in R with core.test. And we're probably going to want just the p-value from that. It's going to give us a lot of other information as well. The p-value is significant. It's less than 0.05. With the E-8 that we're seeing there, that's basically saying 1.29 times 10 to the -8. This means you move the decimal, what, 8 times? That means there's 7 zeros there. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So actually, the p-value is less than 0.001, which means that this linear correlation coefficient right there, 0.70. It's very significant. Yes, we have strong evidence that these two variables are linearly correlated. Now, in terms of how would you categorize that? Um, the categories really depend on how they're defined in your specific course. For me, ours is in between 0.60 and 0.79. So the 0.70 is in between those. We're categorizing that as strong. So the linear relationship is strong. Okay. Now, in terms of getting the R squared value for the model, the linear model, that's kind of the next thing you would need to know about how to do that in R. In R, let's go into R here. The way that you're going to want to do that is you're going to want to put these two data sets into a data frame. So you're going to want to use the data frame command, and I'm going to call my data frame df. And I'm going to just put, now you put them backwards than you did earlier because you're saying gene expression, PE. That's what I'm interested in. And I want to know, you put a little tilde there. You say, hey, how does gene length affect that? And you give R your data set. And, and, um, and sorry, I'm jumping the gun here. I didn't finish the, all right. So the data frame, sorry, I'm just moving too fast, is gene length, gene expression, or expression level. Um, that's just the data frame. I mean, that if we hit DF, we can see it just puts them into two columns. So yeah, data frame first, I was jumping ahead of myself. Now the linear model, we want to put that into X, and that's the one that comes backwards because you're saying, hey, gene expression level, that's the one I'm interested in. How does gene length affect it? So gene length comes second because in R, sometimes you say, hey, how does gene length affect it? How does the weather affect it? How does how does how do the clouds affect it? So all the things that affect it, you put it in the back. For us, we only have one. It's gene length, and so that goes in the back. And we would like to get just a summary there. And this summary, uh, we can see our adjusted R squared value right there. So let's go ahead and mark that down. We have our adjusted R squared value. And what does that mean? It means that 48% of the variability so all of the variability that you see in the data, it's varying, right? All of the data variance from the expression level, out of all of it, 48% of it is due to the variation in gene length. So that means gene length is kind of a big culprit here. Gene length is causing a lot of the variance going on here. To cause 48% of the variance alone, just on that one variable, that means gene length is it's involved. Gene length is a cause of a lot of variance in the expression level. So that's what we're looking for with the R squared. Now, the linear model in two decimals, that's where we're going to say, hey, we want to basically write an equation that predicts the expression level, where we have a y-intercept, and then we have some amount of some sort of coefficient for gene length. So if a person would come in and give us a gene length, say, hey, the gene length I found in the lab is 1800, you would multiply that by this number and add the y-intercept, and you would say, oh, well, I predict that the expression level is blah, 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 So if a person would give you the gene length, you would multiply and then add. Now, if you see an R, the weight, I'll highlight over here where you get these. So 1.05 times 10 to the 2, we shift that decimal 2 times, we get 105 for the intercept. For the coefficient of gene length, we would need to move this decimal 2 times to the left. So 0.04825, or as the worksheet says, it says give 2 decimals. So let me correct this and say 0.05. Okay, and now we can predict, as number 6 asks us to do. It says predict the protein expression levels for these specific gene lengths. It's like, okay, we can do that now. We say 105 plus, and I'll just use the 0.05, even though it's a little bit lacking in accuracy. Okay, gene expression of 1900. Oh, we would get a protein expression level of 200. If somebody said, hey, the gene length is 2100, okay, we can do that. Our protein expression level is 210, and so on, 2300. So the predicted values for these 3 gene lengths are the protein expression levels 200, 210, and 220. So let's just review all of that. That's kind of the basics. Let me grab a darker color here, and let's just review what we did here today in R. Let's see if I can't just go to let's stop the screen share and just look at the worksheet itself. We got the linear correlation coefficient. We use the core command to do that. It's very important to get your linear correlation coefficient. Then we tested whether it was actually significant. It's one thing to get a correlation. The computer will give you a correlation for any data sets, but is it significant? Core.test will tell you that. Categorizing it as strong, that depends on your specific scenario. In my class, we have a specific table that kind of tells you, it takes a number, it gives you some English language. Oh, that's strong, that's weak, that's moderate. The R squared value is now that was the line in the video, the linear model. If you need to go back and pause that, that's a particular kind of thing you have to set up with a data frame. Then the linear model, if you want to write it as an equation, so you have basically a response variable, and then you have a y-intercept plus some sort of coefficient here multiplied by your dependent variable. Or sorry, I got this backwards. This dependent variable, independent variable, let's say. And then in order to predict after that, I mean, you need to just have these coefficients, you round them to whatever you need to round them to, and you plug in specific values of the independent variable to see your prediction. So the whole idea of correlation coefficient, or sorry, regression, linear regression, right there, linear regression is that we're going to predict. We're going to try to predict, because if something is linear, then we would draw kind of a this line of best fit, and then we would do prediction with that.